Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Guillermo and I chat with Ying, Tong, and Bryan Gillespie. We get to know both of these researchers and what brought them to work on ZK specifically. We talk with Ying Tong about her work on Zcash, working on the Halo 2 system, and some of her subsequent contributions at Geometry Research. We learn from Bryan about his journey to working on ZK, also via Zcash, and his work today at Inversed Tech. We then dive into their recent work, which examines programmable privacy in distributed systems. We tease out the classifications and framework that they introduced to better evaluate and compare different applications that offer limit order auctions using ZK or related technologies. Now, before we kick off, I just want to let you know about our upcoming event, ZK Hack Montreal, happening August 9th through 11th. In case you don't know, ZK Hack is another project that I'm involved in. It's a hub for ZK learning, which is very much community-driven. And as part of this, we produce virtual as well as IRL ZK-focused events. The next one of these events is ZK Hack Montreal, bringing our IRL hackathon series to my hometown. Now, ZK Hack Montreal will be happening, as mentioned, August 9th through 11th, and it promises to be a very special one, being the first time we host our hackathon series in North America. Some of you may be attending SBC the week leading up to the ZK Hack weekend. Luckily, it's just an hour flight from New York to Montreal, so you can easily do both events. Plus, you get to hang out in beautiful Montreal for the weekend and hack on ZK tools, meet experts in the field, and maybe meet your future collaborators or co-founders at ZK Hack Montreal. You can apply and also find out any updates about partners and judges over on zkmontreal.com. I've added the link in the show notes. So yeah, we hope to see you there. Now, Tanya will share a little bit about this week's sponsors.
Aleo is a new Layer 1 blockchain that achieves the programmability of Ethereum, the privacy of Zcash, and the scalability of a rollup. Driven by a mission for a truly secure internet, Aleo has interwoven zero-knowledge proofs into every facet of their stack, resulting in a vertically integrated Layer 1 blockchain that's unparalleled in its approach. Aleo is ZK by design. Dive into their programming language Leo and see what permissionless development looks like, offering boundless opportunities for developers and innovators to build ZK apps. This is an invitation to be part of a transformational ZK journey. Dive deeper and discover more about Aleo at aleo.org.
And now, here's our episode.
Today, Guillermo and I are here with Ying Tong from Geometry Research and Bryan Gillespie from Inversed Tech. Welcome both of you to the show.
Hi, I'm so glad to be on ZK Podcast.
Yeah, it's awesome to be here.
Hey, Guillermo.
What's up?
So Ying Tong, I feel like this episode came about because, we started talking about having you on. I've known you for a few years, but I'm really curious to find out from you, what got you excited about cryptography in the first place? What was the thing that brought you to work on these kinds of problems?
Well, I was trained as a physicist, and I really got into cryptography via the Ethereum project and just the shared hallucination of a world computer. And when I first joined the Ethereum Foundation, I worked with Barry Whitehat on implementing, I think, one of the first ZK rollups.
Oh, cool.
From there, that was the gateway drug really into zero knowledge. And when the Zcash team published their findings about Halo and recursive proofs without succinctness, that got me really excited about the possibilities of zero knowledge. I joined Zcash, worked on Halo 2. Really, a lot of the workshops and educational outreach was centered around Halo 2, and that was really fun, really productive. And I'm continuing that journey now at Geometry Research, as well as continuing to work on these problems of programmable privacy, the design space that Zcash remains very interested in.
I had not realized that you had actually first started at Ethereum and then worked at the ECC. I remember meeting you, I think it was for like a ZK summit you gave a talk, and at the time you were more part of the Zcash world. Going back to that like early experience at Ethereum, though, like how did you connect with those folks coming from like physics?
That was about to be my question. I was like, a fellow physicist, you know, how did you come to the dark side or the light side, depending on how you look at it, I guess?
Well, the Ethereum Foundation had a headquarters in Singapore where I was studying, and they came around my school recruiting not just computer scientists, as you would expect, but also physicists. They explicitly stated that they wanted physicists. And I think a lot of the physics training is not directly transferable. However, the reasoning skills and the ability to pick up new concepts with a high level of rigor, I think were very valuable and helped me a lot in learning cryptography and zero knowledge.
Nice. That's so cool. I want to come back to, for example, like the Halo 2 workshops and stuff, but I want to first ask Bryan to share a little bit about his background. Tell us a little bit about what you've been working on and why you got excited about this.
Yeah, absolutely. So I'm coming from the other side of theoretical academic backgrounds. I have a mathematics PhD and eventually decided that cryptography was the best thing ever.
Cool.
I too have a connection with the Zcash side of things, the blog posts by Ariel Gabizon and others on the SNARK technology in Zcash was one of the first things that inspired me to start looking in this direction. Kind of the first and second year of the pandemic, I realized that this was just the coolest thing ever. And so I took the time to pick it up and learn some of these things. Taught a one semester course, upper division undergrad at the university near me. And then I got a job through Twitter.
Through Twitter. Nice. What kind of math were you doing before, though?
So my PhD was in the area of algebraic combinatorics. This is looking at kind of discrete mathematical objects, so objects that you can enumerate and count, and trying to understand them by looking at algebraic constructions like polynomial spaces and more complicated things you can say about them. And so it actually really relates a lot to the constructions that you run into in ZK technology. I'm finding that actually my background really relates fairly well to the sorts of things that we do when we're studying zkSNARKs or multi-party computation or other types of cryptography that you're encoding data into these mathematical forms.
So cool.
So, random quick question. So, like, just to get a little bit more of a sense, like algebraic combinatorics would be things like generating functions or generating polynomials would be like one object that you might study in this particular field, I assume.
Yes, absolutely. And the idea is to use kind of heavier algebraic constructions, like people talk about algebraic geometry as a basis for cryptography. You can also use algebraic geometry to understand these other discrete objects in a really kind of deep and useful way.
What was the first company or project that you got involved in when you jumped in?
My current job is actually my first job in the space.
Oh, nice.
Aside from that course that I mentioned earlier, that I taught at university. So Inverse Tech, it's a relatively recent cryptography consulting upstart. And I just reached out on Twitter and said, hey, just wanted, in case there's anybody out there looking for somebody with my background, to say that I'm available and looking for work. And my boss, Daniel, reached out and we got in touch.
Nice.
Incredible. Don't just let your dreams be memes. It's very important that you really can keep posting through it. I love it. An inspiration for us all.
Absolutely.
That's amazing.
I think this was before Twitter became X, but the point remains.
It's still Twitter in our hearts, I think.
Yeah. So this is Daniel, who was also one of the people who kind of started the ZK Proofs event series. He used to be part of a group called Kedit. But yeah, so I mean, we've known Daniel for a long time. That's really cool that you landed there. What kind of work do you do at Inverse Tech? You sort of mentioned it's consulting, but like, is there any particular problem spaces you're tackling?
Yeah, it's a really wide variety of different specific types of work, but broadly, it's in the privacy space.
Okay.
We're really interested in contributing to open web technologies that present opportunities for people to maintain their personal privacy. So this research project that we're working on for programmable privacy is part of that, and helping out with other technologies that are trying to provide people with the opportunities to stay private and keep their data out of the panopticons out there is really like a big part of what we care about.
Cool. All right. I want to now circle back to you, Ying, Tong, and talk a bit about those Halo 2 workshops that you mentioned. Because to me, like when you were hosting those, I think you were doing it with the zkSNARKs folks, right? Like, I think your workshops influenced a whole batch of projects who have since at least started building on Halo 2 after learning it from you. I just want to go back to like how that workshop idea even came about, what it takes to put something like that together. Like you were part of the team that developed it. So I imagine you're in it, like you're already deep in it. But yeah, what did you have to do to that material to turn it into a workshop?
Yeah, I think Xerox PARC has this incredible energy for finding talent and making these resources available to them. And really, I was just one person in a really motivated team. So yeah, what it took really was just reaching out to people. A lot of them came from universities. A lot of them came from like the open source projects that we're already familiar with. And just a lot of like random hackers as well. Preparing the resources and just getting the people together to show up every week, be it virtually or, at a physical location. We had a few pop-ups in New York City as well as Boston and San Francisco. And it was fueled by this enthusiasm and this sort of eagerness and willingness to learn, to explore, to build together. So at that time, yeah, Halo 2 was perhaps one of the more advanced ZK proving stacks out there. And since then, we've had lots of variations on the original Halo 2. We've had significant forks that are popularly adopted. And we've had completely new proof systems become open source and available, such as Plonky 3, for example. So yeah, I do hope that this culture of learning and sharing continues to grow. And I'm very excited for the next generation of proof systems. And I'm excited to see, for example, client-side proving become a reality. Definitely this tradition of building in the open and sharing information and resources with each other is something very precious in this space. And I look forward to seeing it continue.
That's so interesting. Yeah, just as an aside, I just today actually met with Zach from Aztec, and we were talking about that idea of like the building in that open way. And I was realizing that we're kind of in this very special moment in ZK where there's like well-funded efforts to build in a certain direction. And then because there's not an air of scarcity in terms of just like people feeling funded and like they're not like scrounging for like being able to live. They actually have the space to live and then they can just do the research they want to do. You've had this acceleration on the ZK front, but it's not replicated in other industries. It's not even necessarily replicated in other parts of like cryptography or math. It's just like this really cool moment where people have been able to drive it really quickly. But I like that because I think it shows something. Like it's kind of an example potentially to other fields that like there is this way that you can accelerate things that you think are impossible much, much faster than you would have imagined. And it's not just by like having big companies do it, which I think in the past you kind of required like the capital intensive large corporation to make something like this happen. Here it's happening from lots of different companies, lots of different individual contributors, people also of all ages who are kind of empowered to do what they want. Yeah, it's really cool.
Absolutely. I think it's a competitive advantage to build in the open and to allow easy adoption of your libraries and your products. And there's so many benefits. For example, more eyes on your code means more bugs will likely be surfaced. That's one of the top advantages of making your code open source. I think as the industry matures, we're moving more and more towards standardization. And having your library accessible means that you're part of the standardization conversation. It means that your tools are not going to be just obsoleted with the next wave. So building in the open, building collaboratively is such a competitive advantage. I think it just makes sense to do it that way.
I do think there's one other piece, and we've brought this up a couple times on the show, but this is about like patenting things and like locking them down. There are even adjacent fields where you see it's just more of an effort to patent early. And I feel like history sort of shows that like a lot of times in fields like this, if you patent early, all it does is like slows down that part of the research. And ZK luckily has sort of like accelerated past any previous patent efforts and other patents like, what was it? Like Fiat Shamir? Or Schnorr.
Yeah.
Like the patent expired and all of a sudden you could use it. And it just like, you saw like this boom happen. I think seeing that happen, play out, should be an example to all practitioners in these adjacent fields that maybe like be careful with those heavy patents. Even if your company is locked down, people may not be able to use your tech in the long run. It's a topic that I'm seeing more and more clearly kind of come into view. And I feel like ZK is the counterexample of like, this is what happens if you don't immediately try to lock this down early, but you actually leave it for like a larger community to play with. Before we move on from the Halo 2 work, I have sort of a dumb question that I'm pretty sure has been answered at some point on this show, which is Halo 2 using Fry? Is there a connection between Fry and Halo 2?
The original Halo 2 uses the IPA, polynomial commitment scheme. So that's Zcash Halo 2.
Okay.
Whereas there have been sort of forks of Halo 2 that have adapted the front end to work with Fry on the back end, to work with small field Fry in particular.
Okay.
So
Nice.
that's one of the advantages of having a modular proving system is that you can swap out the back end. And you can, for example, put in different lookup arguments. You can put in different fields, different polynomial commitments. But the original Halo 2 used the IPA polynomial commitment.
Okay, this might be why actually I didn't know the answer to that. It's like I probably have asked. Maybe back then it didn't use Fry, but then I've heard it did use Fry. Okay, this is exactly why. I don't know if you're still following that, but like, did you see the stir work?
Yes.
Yeah, I'm just curious if you have any like thoughts on it, given that it is sort of interrelated with some of the Halo stuff.
I've heard that stir can just work as a drop-in replacement of Fry. I think it would be really a great improvement if someone were to implement that. I will say one caveat. It's also why standardization is so important. So when composing different elements from across the proving stack, we have to make sure that certain security invariants are preserved. For example, whether or not your commitment scheme preserves zero knowledge. So these questions are what standardization efforts aim to guide and aim to provide a template for. But in general, it's been inspiring to see just the amount of experimentation that's been done on Halo 2. Yeah, there's really any number of backends that have been swapped in Halo 2, even like multilinear backends.
What was the system that you feel like captured mindshare after, just in terms of like the chronology of it, like just timing wise?
What's caught my eye is Plonky 2, Plonky 3.
Okay, that group, yeah.
Yeah, for example, I think SP1 and Valida both use Plonky 2 or Plonky 3. I think really the speed ups from the small field optimizations are very compelling. I do think that Halo 2 belongs to an earlier generation of proof systems. I would like to see how Halo 2 can be adapted to newer proof systems that are more efficient.
By the way, very dumb question. When you say small field fry, like what does that mean? Is it like a small prime that's like below to the 32 or something, or is it like some binary field? Like what is a small field? I guess in this case, just for the people who have very little idea what zk is.
The small field really can go down to 32 bits. That's the baby bear field that RISC-0 uses, for example. And it's called a small field because we're used to working with 128, 256, or 381-bit fields in cryptography. Fields over which the short Zippel lemma is sort of very secure, whereas small field fry pushes the boundaries of that. And the reason they're able to get away with that is that they don't rely on discrete log hardness. They don't rely on having access to a cryptographic group. And because they just use simple post-quantum primitives, namely hashing, they can get away with very small fields that are efficient on most computer architectures.
So I want to shift gears a little bit and start talking about a recent work that you released. It's focused on programmable privacy in distributed systems. This is also partly where this episode comes about. Ying, Tong, when I reached out to you, you were like, let's talk about this work. And we are bringing you on, Bryan, to kind of cover this. Yeah, I want to sort of dive into what this is. To me, it reads a little like it's a really good explanation of a lot of the ways of thinking about different systems, the choices that you're making in order to like actually evaluate various projects, like companies using variations on some of these systems. I think of it as like a bit of a survey. So yeah, tell me a little bit about this work. What was the motivation? Where did the idea come from? And then we can dig into some of the topics that you cover.
So this SOK originated from the Zcash Foundation wanting to explore options for introducing programmability onto Zcash. And really this survey was to get us up to speed with the state of the art in the industry and also to make recommendations for the path forward for Zcash.
Got it.
So in my mind, there's kind of 3 flavors of programmable privacy that are sort of dominant in people's minds. The first one is this idea of selective disclosure, meaning that you can program what you reveal and to whom. So sort of the logical conclusion of selective disclosure would be witness encryption. Like you specify exactly what condition someone must fulfill in order to decrypt some data. And this metaphor of selective disclosure, to me, is closely related to purpose limitation and access control, which might be more familiar metaphors outside this industry. And the second kind of programmable privacy is you're programming the attributes that you verify about private data. So, for example, in Zcash, we want to verify ownership of a note. We want to verify that the note hasn't been spent before. We want to verify some range checks on the value of the note. And Aleo or Zaxi generalizes this statement to basically any NP relation. So programmability in the sense that you can verify whatever you want about private data. And this is also the notion that's used in Aztec and Mina, for example.
Is that still in the second category? You have the first one with selective disclosure. The second one is this like attributes, but like
it's
to me,
like programmable verifiability.
Okay,
basically.
programmable verifiability. So you are putting Aztec, Aleo all in the second category still?
I am.
Okay.
And I'm also putting all ZK rollups in there.
Oh, wow.
As well.
So what's the third?
The third one is programmable computation over private data.
Oh.
So you think like homomorphic encryption, FHE, MPC, that you have some structured encoding of your data on which you can actually perform any arbitrary computation. And this third category was actually the focus of our paper. We call it the mediated computation phase. You'll hear more about it from Bryan later. But yeah, these are the three sort of metaphors for programmable privacy that are the most common in the industry.
I think it's really good that you just teased out those three too, because programmable privacy, I've heard that referred to lots of different kinds, and I think it's cool to see them really outlined here. You focused on this programmable computation over private data, and you sort of mentioned some of the other systems like MPC, FHE that are used for this, but I know that in the work you also do highlight ZK projects. So I guess there is a way to do this even in ZK systems. Is it more complicated? I know we're going to probably get to that, but like, does ZK actually offer an advantage or disadvantage when you're trying to tackle this problem?
So I think that the real bottom line is that ZK is a powerful toolbox for doing a certain type of computation, which is private off-chain computation where you have access personally to the private data that you're computing over. So in some sense, the ZK class of protocols allows generic computation over your own private data. But what we found is that there's kind of a different class of cryptographic techniques. We mentioned FHE and secure multi-party computation and different approaches.
And maybe even TEEs?
Maybe even TEEs. Yes. A little bit of a complicated debate over their usage, but there is a usage for them. But which allows computation over private data from multiple parties. So the real distinction is whether you have the ability to do this computation in such a way that the compute nodes themselves can't see the private data, which is very relevant in a lot of DeFi sorts of applications in particular, where you need to kind of combine these pieces in a synchronous way from multiple parties.
When you say off-chain, do you mean client-side? Is this like the proof and all of the privacy is remaining in the hands of the individual? Or do you mean like it's in the hands of this off-chain system, but it could still be shared?
It's kind of both, actually. zkSNARKs, I view them as kind of a glue between different regimes of trust. So one computational engine can do computations, and in that computational engine, you know certain things. And then you want to relay that to a different computational engine, say the on-chain, blockchain, virtual machine, or something like that. The SNARK proofs allow you to demonstrate that the computation was done correctly without revealing any more than you need to. It's a connector between these different computational engines that allows you to separate out the different privacy regimes that are important.
So this work in particular, when I started to read through it, like your focus was on limit order auctions or DEXs more broadly. I don't know if you know this, but like Guillermo, who's here with me, when we met, it was in 2021, and Guillermo, Alex, and Tarun had done some work kind of almost like debunking that you could even have a private DEX. But like now in your work, you definitely showcased that like there are efforts to do that. Guillermo, I don't know if you want to weigh in.
Yeah, I mean, it was the original version of it was just, remember people being like, oh, just, take a DEX and just like put privacy on it, like like the Elizabeth Holmes do a chemistry like version. That was like cool, but like it just totally doesn't work because you can just like back out from like really basic information what the underlying thing was. Of course, in that work we suggested some random things like you should batch together trades, and that will give you some guarantees, depends on the size of the trades, blah blah. And then we have a different work suggesting a like even crazier method, which like cuts up a trade and then does a bunch of stuff and like blends it together using some PRNG, and then like you have some differential privacy, which is like that's like super.
That was the differential privacy was sort of your.
So that one gets like quite deep into the like very lost in the sauce in that case. But it's much it's the like if you don't have this nice batching, you have like a little bit more annoying type of thing, like how do you do it? And then Penumbra was also similarly, I think, after this work was Henry realizing that you can use kind of these, I believe it was some partially homomorphic encryption to kind of construct these batches automatically. And so you actually really can get like private batch kind of exchanges. But it has weird properties. And so we have another paper analyzing like what that means for like arbitrage. But anyways, the point is, yes, it's very funny. This is actually how we met. And I feel like we've come full circle on this one. It's this is like a callback,
Yeah, we saw this batch auction design in Penumbra, as you mentioned, and interestingly enough, also in Secret Network. Basically, any implementation of an AMM where the prices are public. So in Secret Network, if you're trading on an AMM and your trade is the only transaction in a block, then it'll be super obvious exactly what the amounts of your trade were.
Yep.
And yeah, it was interesting to me that it's the same batch anonymity set guarantee as Penumbra. So in Penumbra, if you're the only one in your batch, similarly, you're not going to get any privacy. Yeah. But I will say that the order book implementations had different privacy properties. So we looked, for example, at Renegade Fi. So they implement an order book DEX where the prices are private, and you run a matching algorithm in a two-party computation. And if your orders do match, then you form a balanced transaction that is submitted on-chain that conceals the amounts of the individual orders. If your orders don't match, then nothing happens. And either party in the 2PC learns nothing about the other party's prices.
Interesting. You just mentioned sort of 3 examples there. You had Penumbra, Secret, Renegade Fi. Was there another project that you looked at, or was it just those 3 that you were kind of comparing in this work?
The final project we looked at was ZSA Swap. Similarly to Renegade Fi, they implement an order book DEX where the prices are kept private. So ZSA Swap is not a real protocol yet. Very much it's in the design phase.
Okay. But that's cool. I mean, let's tease out even more the differences between these. And I know because you also introduced these other ways of thinking about computation. I don't know if each one of these projects uses a different type of computation or if they're all kind of playing in the same area. But yeah, maybe Bryan, you can share a little bit about those 3 categories that you had in there.
Yeah, absolutely. So we've mentioned all 3 of the techniques that these protocols make use of right now. So the Secret Network is leaning heavily on TEEs, or trusted execution environments, which are secure hardware enclaves that allow computations to happen in a privacy-preserving way because it's very difficult to exfiltrate any data of any sort from within the hardware that's doing the computation. Some people have discussions about how much one should trust the hardware implementations from companies that maybe don't have the best track record of having totally bug-free hardware. But in many cases, this trusted execution environment approach is very effective at just keeping a trustless network from having to trust too much.
Yeah.
And so Secret Network does all of their main computations in the trusted execution environment, and that's how they allow private data from multiple parties to come together. The Renegade Fi approach is a really interesting one because it uses secure multi-party computation. And these are cryptographic techniques that allow different computational nodes to use mathematics of polynomials and cryptosystems to combine their data in a way that nobody sees anything except the expected output of the computation. It's really quite magical. The downside is that there are some inefficiencies in doing these sorts of computations. A lot of communication costs in particular between the parties tend to add up. But Renegade Fi's approach is just to do a secure multi-party computation between 2 different parties. This is another aspect of their protocol, which is limiting. 2-party computation is often reasonably doable. If you want to do computations with more parties than that, then it gets complicated. But it does a really good job of doing a particular matching protocol for limit orders, and it kind of accomplishes the privacy characteristics that they're aiming for very well. Penumbra is really an interesting protocol from my perspective. What I really like about it is it puts together just the smallest kernel of computation in this what we call mediated computation phase. It's just a little part that allows you to do something with private data from multiple parties to achieve this differential privacy that Guillermo was mentioning earlier. And so all it does is it takes the requests for trading some type of asset for another type of asset, and it adds them all together in this very small multi-party computation. It's just a threshold decryption scheme. And so everybody encrypts their amounts to the same public key, and then a threshold of validators are required in order to decrypt the outputs after they've been added together. So kind of all of the trades that happen at the same time are added together before they're decrypted. And so it relies on kind of the validator set not deciding to decrypt early as a group. But trusting a group is easier than trusting any individual validator by themselves.
So a quick question. You alluded to this this part. I don't recall what you called it. It's mediated computation.
Yep.
I think you have this very nice framework in the paper, which I really appreciated, which is like it seems that all of these protocols, kind of the way they work, if I recall correctly, I could have misread this, is they have kind of three phases, right? For how they're doing it. And I thought this was a lovely framework. So if you want to just go into how they all have the same structure, that I think is a really lovely framework for thinking about these things.
The real big picture here is that there are different cryptographic techniques that can accomplish different effects in this distributed trustless space. Ethereum started out by exploring kind of the public replicated virtual machine, the global computer, and no privacy properties included. And then this kind of ZK thesis of chains allow off-chain computation to occur because of either specialized signature schemes or general zkSNARKs, which allow you to verify computation that happens off-chain. And kind of these two regimes of computation have a lot of study put into them and kind of have well understood cryptographic properties. But then there's something else that's needed to combine private inputs from multiple parties. Like those two techniques can't accomplish this by themselves. And the problem ends up being that the techniques to do this are difficult. They're complicated, they're subtle, they take a lot of cryptographic sophistication to implement properly. And so what we found is that most computation should be put into the zkSNARK off-chain computation side or the on-chain global computation side for purposes of cryptographic suitability and for purposes of computational efficiency. But new privacy chains are incorporating kind of some special sauce of some sort. And generically, what is needed is a separate step in kind of forming a block or forming a new computational unit, which does this extra task of combining private computations or private inputs from multiple parties. And so what we realized is that how blockchains are doing this is starting with off-chain, doing some kind of mediated computation phase, which either is some separate protocol that's not even related to the blockchain that it's ending up on, or perhaps is something that's provided by the blockchain, by the validator set, or by some separate software that validators also run, in order to combine these inputs and then produce something that can be ingested by the on-chain systems for computation.
Yeah. As Bryan said, we noticed this structure of 3 phases: independent, mediated, and global computation. And the independent computation happens off-chain where only the user's private data is involved. And the global computation happens on-chain where the consensus and the network's validators are actually verifying, actually guaranteeing the correctness of the state update. And we noticed where these protocols differ most significantly is in the middle phase of mediated computation.
Oh, wow.
And the scarce resource here always is the network validators. It's the resources that the whole consensus has to be involved in. And for example, Penumbra actually involves all of its validators in this threshold decryption effort. Secret Network as well. Every validator runs a TEE. Whereas if you look at ZSA Swap, they relegate the mediated computation chain to some off-chain solver that is not creating this extra strain on the network's resources. But at the same time, the privacy guarantees that the users have are solely depending on this off-chain operator. So we did notice in this three-phase structure that there is a trade-off happening in the middle phase of privacy versus expressivity, that if you move your private mediated computation off-chain, you're free to perform a more expressive, arbitrary computation. But your privacy guarantees are weakened, and they rely on some entity that is not secured by the network's consensus and by the network's economic security. Whereas if you choose to perform the mediated computation on-chain, you are placing burdens on every validator in the network, burdens of synchronicity, burdens of compute. But from that, you get this very strong privacy guarantee, for example, a K of n threshold guarantee that you wouldn't get in the first case.
Oh, that's an interesting finding. So you're choosing the sort of privacy expressivity axis, but are there any other characteristics? Like, is there any like security or like, is there other things that get affected by the choices that are made here?
So one of the interesting characteristics of these systems that we observed is that very conveniently, the design can be put together so that the privacy properties are the main thing that is on the line for how the mediated computation is designed. Generally, because computations are consumed at the consensus layer using some kind of proof scheme, the correctness of the applications involved is not at risk.
I see.
So when you're looking at the mediated computation techniques, a lot of the question is it possible for this private data that users are submitting to be revealed to the compute nodes or to other parties?
Okay, cool. So it's like how private is going up and down depending, but the proofs are still proofs.
That's right.
Another trade-off that we noticed was expressivity versus security, but on the developer experience level.
Like how easy it is to add a bug or not, kind of by accident?
Exactly.
Okay.
The more freedom, the more access you give the developer to these low-level privacy primitives, the greater the chance that you expose them to a foot gun or some pattern that is unintentionally disclosive. So, for example, if you let them vary the size of the encrypted inputs and outputs, that could leak information on what these inputs and outputs are. If you let them vary storage access patterns, for example, and your usual almost side channel attacks on timing, frequency, the size of queries. Another possible example is this branching pattern, whereby, let's say in an auction, in a private auction contract, you have some winning bid that is updated every time a higher bid comes in. So how you would naively implement that is if the new bid is higher, then update the secret bid. But the very fact that the commitment to the secret bid has changed tells me that the new bid was indeed higher than all the other bids. And so patterns like that are trivially disclosive may be exposed with a too expressive interface.
Oh, wow.
And this is true as well in MPC. You can write trivially disclosive MPC circuits. So yeah, this is another trade-off that we noticed. It was not the focus of our paper, but I would say for all practitioners and for anyone who's actually writing programs on these programmable privacy systems, this is absolutely priority for developer experience and for user privacy.
Yeah, I honestly think that it's an important research priority to try and identify good design patterns and good language designs, which make it harder for developers to introduce these sorts of bugs, and also to understand the kind of computational engines that go along with difficult to introduce bugs systems.
After this exploration, do you have any strong opinions about how languages should be designed to avoid such things? I don't know, any like high level, like here are some invariants that like it would be very cool if, your compiler would check for you or your type system would check for you. So I have no idea. But I'm curious.
So we actually made a start on UC style definitions of a bunch of protocols in our SOK. UC means universal composability.
Okay.
And it's a simulation-based proof paradigm. Basically, it simulates the view of an adversary in an idealized functionality versus the real-world protocol, and tries to ensure that the adversary cannot distinguish which version it's interacting with.
Mm.
So we made a start on UC style definitions, but we didn't actually get to UC proofs. I do think that an interesting line of further work would be to look at UC proofs and to look at them in a machine checkable way. So if we could somehow write our programs in terms of their UC ideal functionality, then we could check the desired information leakage and check these privacy invariants.
This would make the coding on like a developer's experience much better because they could have something to just like make sure it catches those things that you were worried might be happening.
Like the compiler could output guarantees about what's actually being upheld versus like things that are being leaked, for example, is I guess what this is
Yes,
getting to.
exactly. If we recenter the developer experience on privacy invariants, then that would make very explicit the information leakage that's intended versus unintended. There is a line of work on privacy notions based on game-based proofs. So this 2018 paper called On Privacy Notions in Anonymous Communication. It defines a bunch of privacy properties. For example, sender-receiver linkability, sender-receiver observability, sender message linkability, receiver message linkability, and so on. It defines this in sort of this tree of implications. And we could make use of these privacy notions and have the developer specify which notion they're interested in preserving and which notions that in turn implies. The Zcash paper also had a bunch of notions around indistinguishability. So as Bryan said, it's a very interesting research question of how to incorporate these notions into DSLs, into interfaces that developers would find intuitive, into interfaces that would be safe for users.
Interesting. I want to just ask a little bit on who the developers here you're talking about are, because in the examples that you highlight, the ones that you really look at, Penumbra, Secret, I don't actually know the other two very well, but like, are you talking to the developers of those systems or developers that are interfacing with those systems? And, we are talking also about this like programmable computation environment. So I just want to make a slight distinguishing of who can make the mistakes, or who are you speaking to with a lot of this stuff?
Yeah, I think the real target audience for these sorts of tools are developer teams that do not have as much cryptographic sophistication as some of the primary developer teams of these protocols.
I see. It's like someone building another system like this.
Yeah, the guys over at Penumbra know exactly what they're doing with all of this cryptography. Right. We're not designing a DSL for them, okay. But more so for protocols that are aiming to make these sorts of functionalities, these sorts of underlying computational engines available to development teams more broadly, who don't have an in-house cryptographer or who don't have a big budget for that type of security, and still want to produce applications that make use of the mediated computation phase. So one interesting point where we see an opening in the space right now is that the main place where real programmable privacy is being implemented in actual blockchain protocols is primarily using TEEs as the foundation. So it's kind of skipping the cryptographic scheme entirely. If you're thinking about multi-party computation or homomorphic encryption, like it's just saying, let's use secure hardware and it'll work. But the problem ends up being that the giving full access to the underlying compute node opens up these sorts of timing attacks or branching logic attacks, and it puts some of the burden of security on the development teams that are using these things. So for instance, the secret network has a really useful and interesting page on things that you should keep in mind for making sure that the privacy of your application is maintained. And it's like very good stuff to keep in mind. But ideally, a DSL would abstract that complexity away from developers so they don't have to think about it.
Cool. You sort of talk a little bit about intents, or that comes up. And I know you, like, the focus was this limit order auction. Maybe that's why that was mentioned. But there was one system that was not mentioned there, which is like Anoma. I know Namada is launching. It's not a DEX. It's not doing that. So I get it. But like, I was kind of curious if you even explored what they're building, or if you really see that as like so different that it wouldn't have fit into this.
Anoma was certainly an inspiration for us in the SOK. The reason we chose limit order auctions as the specific motivating example was to just minimize the complexity of the applications that we're studying, as to capture a minimal set of functionality that's still non-trivial. So as far as I understand it, the privacy of intents on Anoma is orthogonal to their main protocol. It's extra protocol, and it's sort of delegated to their solvers who are matching and solving these intents off-chain and then submitting them as balanced transactions on-chain. So in that sense, Anoma is similar to ZSA swaps, Zcash shielded asset swaps, in that the privacy of the intents and the actual mediated computation of matching and solving them is off-chain or extra protocol.
Got it. Cool. So I feel like, I mean, I've reached the end of the questions I had on particularly this work, but like now that this work is completed and you're kind of like looking forward, where do you see a lot of the systems that you just described, like the MPC and the ZK and the interactions and this sort of mediated computation area? What do you see kind of coming from there?
One outcome that we want from this work is to further discussion on best practices and safe designs in programmable privacy systems. So one trend that we did notice is that zero-knowledge proofs are used as a primitive in almost every one of these designs. So, for example, in Renegade Phi, the matching algorithm is carried out in a two-party computation. But both parties at the same time also produce a collaborative zkSNARK of the validity of their computation. And this is posted on-chain and is publicly verifiable. So we see this again in FHE, where the encrypted input is accompanied by a proof of correct encryption, so that the validator nodes know that they're not receiving garbage, that they're receiving some input that was actually properly encrypted to them. And lastly, in TEEs, we've again seen proposals for getting the TEE to run a ZK prover and basically removing this dependency on the TEE for integrity. So we're limiting the responsibility of the TEE to just confidentiality, and we're asking it to produce as a publicly verifiable ZK proof so that anyone outside the TEE can check that it actually ran the program it was supposed to run. And there are multiple other ways to stack these primitives. So defense in depth, best practices. This is one of the sort of outcomes we would like, one of the takeaways we would like to communicate with this work. Programmable privacy systems actually consider how they can make full use of these different cryptographic primitives.
Nice. I mean, it's interesting because like the combinations of the ZK and FHE, ZK, MPC, we've covered on the podcast before, but it's interesting here that like you're positioning it much more as like ZK being used as a tool and not necessarily, because I mean, we've also seen like MPC be used in a ZK scenario if you talk trusted setup or something like this. But here you're sort of saying like in the MPC itself, you're using the technique of ZK to like prove something about some computation that's happening in that private environment often. Yeah, I like thinking about it in all of those ways. That's cool.
Yeah, that's cool.
Before we sign off, I want to hear a little bit about maybe other future work that you yourselves are working on, like kind of directions that you want to explore even further beyond what we've already talked about on the show.
So one of the directions that I think is really interesting that I would like to spend some time investigating at some point is looking at, in particular, more dynamic MPC-based mediated computation. So using multi-party computation with a trust based on a threshold of the compute nodes to provide some general computational functionalities. Like in particular, where you see MPC used in a lot of protocols right now is very specialized functionality, threshold decryption or some particular circuit that needs to be computed. And it's part of the reason for that is that you can really optimize the multi-party computation in that context to get good efficiency and good security properties. But I don't think that people have spent enough time thinking about efficient generic computation in MPC and how that can be used to really accentuate the privacy properties of these systems for distributed blockchains.
Cool. What about you, Ying Tong?
I'm actually interested in a taxonomy of classes of applications that would benefit from programmable privacy, and relatedly, the best practices and the privacy-preserving design patterns that correspond to these different classes of applications. In this SOK, we chose to narrow our focus to limit order auctions. And I do think that covers a great deal of interesting dynamics in programmable privacy. But yeah, I think it would be really interesting and really valuable to define more generally the types of interaction required by different classes of so-called privacy-preserving applications, and then correspondingly the cryptographic primitives that they require at the minimum to realize.
That's interesting. I was actually going to ask you exactly that about like looking past just the limit order auctions. But can you just share like maybe a handful of types that you have already identified even? Like what would they be called? Are they always in the context of like dexes or like trades, or would it go into stuff like message passing or something like that isn't dex related?
I've seen lots of applications that are hidden information games. So someone once described it to me as you're hiding in a bush and I throw a spear at you. And I want it to be reflected in the global state that this event happened and that your health decreased.
Oh, okay. Like for a game, I guess. Yeah.
Yes. So, well, games are so useful in surfacing these dynamics. Well, another application that's interesting to me is MTCS, or Multilateral Trade Credit Settlement. And this is sort of extending the interaction to sort of a cycle of participants instead of just pairwise. So this sort of atomic settlement in a cycle of participants, yeah, it's an extension of what we've studied in this paper. And I guess we came across a bunch of applications that had really fewer requirements. So they had only commutative updates. For example, I think voting, you can achieve that just using zkSNARKs. Each time you're just like adding something, a +1. Auctions, you could do that similarly. So yeah, there's certainly applications with greater and lesser requirements on interactivity of private state. But I haven't quite seen a rigorous classification of them yet. So I'm very motivated to make one.
Cool. That's awesome.
Sounds fascinating.
And maybe that will be something we can talk about on a future podcast.
Yes.
Nice.
Dun, dun, dun.
All right. I want to say thank you to both of you for coming on, sharing a little bit about your backgrounds, what got you excited about this work, and then obviously our dive into the programmable privacy and distributed systems, SOK. Yeah, it was so great to have you on.
Thank you for having us on. This was lots of fun.
Yeah, it was awesome to be here.
Yeah. Thanks, Guillermo.
I'm just here. Don't mind me.
All right. And I want to say thank you to the podcast team, Henrik, Rachel, and Tanya, and to our listeners. Thanks for listening.